So, in this video we are going to continue from where we left in the earlier one. So, in the last video what we had done was we had looked into the Banyan networks, their essentially basic definition, and we had also looked into how you can actually create a delta B network. So, delta B network is a special subclass of a Banyan network configuration. So, Banyan network are the networks where there is exactly one path from any input to any output. So, all input output pairs will have a different paths and they are bound to be blocking networks by design. Delta networks has only one specific property, that at any stage in any switch all the inputs which are coming to that switch will be coming from the same output levels. So, it may be from the previous stage all output zeros of every switch, or some of the switches it will be coming to the same input. So, or it may be 1 or 2. So, if this property is just being taken care of in the structure, we will actually have digit controlled routing networks, or we also call them delta networks. Okay. We had also looked into how many switching elements will be required in a delta network, which is a symmetric ones, say n by n or a raised power k by b raised power k kind of thing switches. So, where number of inputs and outputs are not same, we have also looked for that scenario. Then I had asked a question that in most of these delta networks, is it possible that can I actually have a same interconnection pattern being repeated between two consecutive states. So, among all stages it is done. Is it possible to build up a digit controlled routed networks? And answer is yes, we can actually do it using a shuffle interconnection. So, let us start with the what is shuffle interconnection, and then get into the proof of that how shuffle interconnect network actually is a digit controlled routing network. So, a shuffle network, shuffle is a pattern, is basically there is an object, collection of objects, I can shuffle them. So, basically when I shuffle I will rearrange, so they will just get mapped in some fashion. So, I have to now define this mapping actually. But before I go to the mapping, let me show you how actually the shuffling happens. So, if there are shuffle actually word has come from the cards, the game of cards. So, when you normally take two stacks out of it, and then you actually take one card from here, one card from here, one after another, and all 52 cards are being put back again. So, that is what is called shuffling. So, basically what you are doing is, for example, if these many objects are there, so these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so let me make it 12. So, I will actually put 2 batches of 6 objects each, and then I will take one object from here, one object from here, one object from here, one object from here, and then one object from here, one 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 from here, and then one from here. And that is what the shuffle interconnection. I have actually created 2 shuffle here. I have created 2 objects, 1 6 objects here, 1 6 objects here. I shuffled them together. So, it is a binary shuffle which has been created for 12 objects. So, in general I can actually define a Q shuffle for Q into R objects. So, here Q is actually equal to 2 and R is equal to 6, Q into R here is the total 12 objects which are there. Okay. So, we will define this Q shuffle as shuffle QR and the entries which I will be making for these QR objects, they will go from 0, 1, 2 and so on till last one will be QR minus 1. That is how we will be indexing the entries. and I can define this shuffled pattern. Basically for any given input identity I should be able to, which will be I, will be my input, I will be able to get SQ star R, which is the index number on this side. So we can define this thing as SQR as function of input, the input index. This will give me QI plus IR mod QR. So let us see what is going to happen if I am looking into this case. Okay. So here actually it is a Q is equal to 2 in this case, there are total 12 objects, okay, 1 2, so I have to count from 0 to 11, that is where my index entry should be there. So QR is 12 in this case, so R is 6, QR is 12. So if I is 0, so 0 into 2 gives me 0, and this is a floor function. So unless I value actually crosses 6, I do not bother actually. So when it crosses 6, I is smaller than R, this value will be 0. When I is greater than R but less than 2R, it will be equal to 1. It is a floor function. This technically means if you put any real number, take a floor thing, this actually means the largest integer lower than or equal to R, where R is a real number. Okay, that is a floor function. So that is what we have been using here. So if I do this, 0 into 2 will give me 0, so I am actually connecting to 0. 0 divided by R, R is 6 here, the floor function is also 0, and modulo QR. Okay. So if I take I is equal to 1, so 1 into 2 will give me 2, 1 by 6 floor function give me 0, so 1 has to be connected to 2, so I have connected to 2. I can take it for value 2 to become connects to 4. Three will connect to 6, 4 will connect to 8, 5 will connect to 10, and when I go to 6, 6 will connect to 6 into 2 12, and 6 by 6, so now the floor function will give me 1. So 12 plus 1 13, QR is 12 and this is a modulo QR operation. So 13 modulo 12 will give me 1. So the 6th one gets connected to 1, okay. 7th one will get connected to 3 and so on, and the 11th one will get connected to 11th. So this is how the shuffle actually is being represented mathematically. Q is equal to 2 is a simple one, this we commonly use this kind of thing in the when we play the game of cards, but game of playing cards actually. We can actually try even for 3 shuffle or 4 shuffle or 5 shuffle kind of things also can be done. So idea is basically you will take multiple objects, okay, and then of course for example I can take 12 of them in this example. Same the way it is actually 4 plus 4, yeah, is a total 12 objects. I can create 3 groups, is a 3 shuffle actually now I am talking about. So R is now in this case will be equal to 4, 4 into 3 QR objects will be 12, and I will be able to map it to again 12 objects. And they are numbered from again 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So I can use the same formula, only thing now Q will be equal to 3, R will be equal to 4. So, once I do this, 0 gets mapped to 0, 1 will get mapped to 1 into 3 actually. So, I am now skipping 2 and then connecting it to the third one, that is what we are doing. Second one will get connected to, so we have to skip 2 and then connect to the last one, 6th. So, 2 into 3 will give me 6, and of course 2 divided by 4, the floor function gives me 0. So, 3 into, so again I have to skip 2 and 3 will give me here 7, 8, 9, 10 and 11. When I come to 4, so 4 by 4 will, the ceiling function will give me 1, 4 into 3 is 12, 12 plus 1 is 13, modulo of 12 QR objects will give me 1. So, 4 gets connected to 1. So, basically you start connect with 0, skip 2, connect with third, skip 2, connect with 6, skip 2, connect with 9, skip 2, next is already connected, so connect with 1, that is what it means. Now, skip 2, this is free, so I connect 5th to this one, skip 2, this gets connected to this one. So, you can actually even count from there that 4 into 3 is 12, so it goes to 1, 5 into 3 is 15, and 5 by 4 floor function gives me 1, 15 plus 1 is 16 modulo QR, QR is 12, so it becomes 4, so 5 is connected to 4. Similarly 6, 3s are 18 plus 1 19, so it turns out to be 7. 7 will get connected to 1, 2, and so 7 will get connected to 10, 8 will get connected to, we count from 11, and then of course I will skip one more. So, this 1 I will not count this 2, so this should be connected to 2, 8 will get connected to 2, 9th will get connected to 5th, 10th will connected to here, 11th will get connected to here, and that is a 3 shuffle. So, similarly I can define 4 shuffle, 5 shuffle and so on. There is an alternative expression also which is feasible. So, I can write QR objects is a Q shuffle, can also be written as Qi mod Q minus 1 n is equal to I when this for 0 less than and when I is equal to QR minus 1. This is another way of expressing the same shuffle thing. So, I am not actually adding this floor function here. So, it is a modulo QR minus 1, sorry, this has to be modulo QR minus 1. So, we can actually even test it from here. So, look at the 3 shuffle, the first object 1 into 3, 0 goes to 0, 1 goes to 3, 2 goes to 6, 3 goes to 9, the fourth 4 into 3 is 12, modulo 11 which becomes 1. So, actually fourth gets connected to 1, and that is what is happening in this case from here to here. Okay. So, this is an alternative form of putting it, and of course, there is one property which we can actually prove, that S of QR, I do it S of RQ, this should be equal to I. So, remember this is R shuffle of same QR objects, and this is Q shuffle. You end up in getting back to the same thing. So, we can actually now use this formulation, I will typically use this formula to actually prove that Shufflenet or shuffle interconnection actually leads to self routing. So, it is kind of a delta network. So, we will be able to prove that having similar interconnection between consecutive stages lead to a delta network if given a certain number of stages. So, we have to show that a raised power n by b raised power n delta network can be constructed using a shuffle between any two consecutive stages So, the network will be of n stages, and between any two consecutive stages I am going to use a shuffle, and what I will get is a delta network. We will be able to construct it. Destination address D we will be now representing by a number. This number will be consisting of, because in every nth stage I will be using one of these destination digits. So, it has to be base b digit. So, I will be using numbers which will be dn minus 1 in the last stage, dn minus 2, d0, this will be in the first stage, this digit will be used, and so on. So, that will be the destination. So, let us see what we will be doing, and normally the way we will be representing this, these switches will be like this. I will have a by b, I will count from 0 to a minus 1, this is the first switch. The next one will be starting with a, this will go to 2a minus 1, again a by b switch. The last one will consist of a raised power n minus a, raised power n minus 1, this will also be a by b. The switches inputs will be numbered in this fashion from top to bottom. I will also be numbering these outputs correspondingly in the same fashion. They will be numbered from 0 to b minus 1, this will be b to 2b minus 1, okay, and last one will be b raised power n minus b, b raised power n minus 1. And then I will be now connecting a shuffle interconnection here. So, these will be numbered from 0 to b raised power n minus 1. I will be doing a shuffling here, and I will get the outputs, okay. And then these again will be connected to a by b and so on. Okay, and then we will have again a shuffle interconnection network and so on till we go to the, this is the first stage 1, stage 2, ultimately there will be stage n, and they will be going from okay, sorry, this will not be b raised power n minus 1, this will be a different number. So, this one will be so that is what will be the number, okay. Sorry, this will not be this. Here you will actually have 0 to b minus 1, b raised power n minus b, b raised power n minus 1, and each one of these will now be represented by a n digit number. Each digit will be a base b digit which will be used as a destination address. So, now the theorem actually which goes is like this. An a raised power n by b raised power n delta network which uses a shuffle as inter-stage link pattern between any two consecutive stages can connect any input to any output given by this by switching the input to output terminal or output port d minus I at each stage I. So, where the labels are being assumed the way it has been shown going from top to bottom. Okay. So, in the first stage I will be using this particular digit, second stage I will be using this, last stage I will be using this particular digit for deciding which output terminal the packet should be routed. So, once this is done I will be able to create a self routing. So, let us start with the proof. So, source S now will be written as S n minus 1, S n minus 2 and so on till S of 0. Remember each one of these digits are base A, that is a digit in that system, base A digit. There will be n such because I am actually using each one of them a raised power n representation. So, there is 0 to a minus 1 value, 0 to a minus 1, total n digits. So, a raised power n inputs can be uniquely identified by this particular digit. Similarly, I am actually representing destination D as which I have written there dn minus 1, dn minus 2, d0 and this will be in base B system all digits. Okay. So, in fact the source S now can be written as a raised power S n minus 1 a raised power n S1a plus S0. So, if I count it in decimal number, this S, the count from the top to bottom. So, I can represent this base A digit number to base decimal number using this expansion formula which is a standard form. So, this what represent the input. In this case S of I goes from 0 to a minus 1. So, these digits can take any one of these values. Okay. So, that is what I am representing where I will be from 1 to n minus 1. Similarly, the D, the digit which is there. So, in decimal this will be now D of n minus 1 b raised power n minus 1 plus d of n minus 2, b raised power n minus 2, and so on till d of 1b plus b0. Okay. So, in this case 0 less than equal to di will now change from 0 to b minus 1. In the first stage I am actually using d of n minus 1 for making the decision. So, if my source is somewhere here, somewhere in between, I call it S, which is represented by this number. So, this number will be now connected to which one of these switches. I need to find out after switching what will be the output number, what is the number here, what is the wire number from top to bottom when I am counting, to which this packet will be routed. Okay. So, this will be now connected to a switch which will be S by A, the lower floor function. So, if S has a value from 0 to A minus 1, it is connected to switch 0. So, I am counting from 0 the when switch numbers, and this will be A raised power n minus 1 switches. Okay. So, when I divide by A, I will get the switch number. So, if S is say 2 and is less than A minus 1, it is connected to switch 0. So, this will give me the switch number multiplied by B. So, if I am actually here, so this B count will be there and remaining will be this number. So, which particular outgoing port will be decided by Dn minus 1. So, the line to which I am connecting, I call it L1. So, L1 will now be represented by S by A, lower floor function into B plus Dn minus 1. Okay. So, Dn minus 1, because that is the digit being used for routing in the first stage. So, I can now expand it, I can put this S from here and divide by A and get the floor function. So, I will get S n minus 1 A raised power n minus 2, I have divided by A, remember. So, this n minus 1 will become n minus 2, this will become n minus 1, this will go away, and S0 by A will be left in the end. So, I will also have S0 by A, and I have to take the floor function of this. Now, this S0 can take a value only from 0 to A minus 1, look here, and I am dividing by A. So, this value is certainly lower than 1, it is a fraction, rest everything will be integer, complete integer. So, when I take the floor function, this will be going away. So, the moment I take floor function, so this will no more be there, this will not be there, and instead, so this whole thing multiplied by B plus Dn minus 1, that will be the number to which the input will be routed after the first stage. Okay. Now, this is going to pass through a shuffle interconnection here. So, now I have to look into the what is the line number. So, I define this thing by as L1 prime after shuffle interconnection. So, I can actually take this L1 and SQR. So, total number of objects I need to know, based on that I will have R, and I have to do A shuffle. So, total number of objects which are present here, total number of switches are these. So, I have A raised power n number of switches into B, that is the total number of ports which are there or lines which are being counted. So, QR is equal to this, and now Q is equal to A. So, which implies R is A raised power n minus 1 B. Okay. So, with these two parameters I can now take L1 and will give me L1 prime. Okay. So, in fact, now I can write as S into A, since it is A shuffle. R now will be given by a raised power n minus 1 b. Sorry, this has to be a minus n minus 1. So, this has to be a n minus 1 b. So, this will in turn will be n minus 2 b r. So, this has to be n minus 2. Okay, into the L1. So, we need to solve for this. So, this will be, so L1 prime will be L1A. I am going to use the shuffle formula, which was S into QR I will use this. So, it will become L1A is A shuffle and I is L1 plus L1 by A n minus 2b mod total number of lines, which is a raised power n minus 1 b So, this is what will be the L1 prime. So, the number of line, so as a shuffling this will be now routed to somewhere here. So, I am trying to find out that line number when counted from top. So, let us solve one by one. So, let me take this floor function first. What is the value of this? Okay. So, L1 by a raised power n minus 2b. So, what is this? So, this remains floor function. L1 is now S of n minus 1 a n minus 2 into b plus d n minus 1. Okay, this I have got from there. I have to divide this whole thing by e raised power n minus 2b and take the floor function. So, when I do this, I still have to keep the floor function first. So, if I am going to look into this particular thing, b will cancel, I will divide by a raised power n minus 2 in fact S of n minus 2 a raised power n minus 3 okay plus if I look here, a raised power n minus 2 is here and n minus 2 is here. I can very well now cancel this term. So, this will go out and I can only use, I can convert it to this thing. Now, interestingly, what is the maximum value of these Sn minus 2 S1? If I look at the definition, Si can go from 0 to a minus 1. So, this is a maximum value which is feasible. So, let us put the maximum values here. So, let us look, this one is complete. So, this will be actually certainly will be there in the floor function. I have to only check for these now. So, if I put a minus 1 here, a minus 1 here for all the terms, let us put the maximum value of dn minus 1, which will be b minus 1 here, okay, and then let us compute the whole thing. So, on computation, so for this part we will have a minus 1 which will be coming as it is out, plus a raised power n minus 3 plus a raised power n minus 4 plus 1 divided by a raised power n minus 2 plus b minus 1 which is the largest value here, okay. So, now for this series what is the value we have to figure out, okay. So, this series consists of how many terms? There is n minus 2 terms actually, it is n minus 3 a raised power 0. So, this is nothing but a geometric progression and I can replace this thing by so series will be first term into this the multiplication factor for every term and total number of terms is n minus 2 minus 1 divided by whatever is a factor minus 1, okay. So, that is what you will get plus b minus 1 a raised power n minus 2b. So, I can now take this, okay, I can write it on the top maybe here. So, this value will turn out to be so this cancels with this one. So, I can put this whole expression here in this and I can write this L1 prime as floor function s of n minus 1 . So, this one actually cancels out, you will have this, and this certainly if you look into this aspect, the numerator is smaller by this much amount and denominator is a raised power n minus 2. So, this has to be a fraction. So, when I am going to take a floor function I should result into nothing but Sn minus 1, okay. So, that is what will be the L1 prime, sorry that is not L1 prime, that is only this particular component, not L1 prime, sorry, and this is only this component L1 by this value. So, I can now replace this thing by Sn minus 1 which comes from there. So, now let us expand this particular term. So, L1 we had already arrived at. So, L1 will be Sn minus 1 into a raised power n minus 2, that is what was the L1. Okay. So, that is L1. Okay. So, this one is L1, L1 has to be multiplied by A plus then I have to do Sn minus 1 . So, this whole thing modulo An minus 1 B. Okay. So, I have to multiply by A all throughout, so it will become Sn minus 1, n minus 2, S1 A B, and this will also be A. So, I can now remove this brace, one extra which has been put. So, now this B can be multiplied with everybody. Now, since I am now doing a modular operation, of a raised power n minus 1 b, so this completes, so this term when doing modular operation will be out actually. So, I can neglect this, I can remove this will not be of any consequence, I need to only look into this particular term. So, maximum value of now I need to find out the modulo, let us see what modulo I will get. Let us put the maximum values of all Sn's, all destination all Sn minus 1, and let us see what I am going to get. Okay. So, this one is going to be maximum A minus 1, so it will be A minus 1. So, worst case value of L1 prime I am trying to estimate. Okay. So, I am only looking into this part, so modulo part we will look into later on. So, A minus 1 A raised power n minus 2 into B so in fact I can take it out. A B, in fact B is I can always take out here. This one will be consisting of B minus 1 into A plus A minus 1, that is a term which is there inside this. So, I am only considering that currently. So, let us now compute this, what I will get. So, this is this one. So, this will be now A minus 1, this is a series which is starting with A. So, this will be A into A, number of terms will be n minus 1, this will be into B, BA minus A plus A minus 1. Okay. So, A minus 1 cancels with this. So, you will end up in getting A raised power n b minus A b. So, minus A b will cancel with this, A will cancel with this. Oh, sorry, this should be n minus 2 terms, this is 1, total A raised power not n minus 1 but A raised power n minus 2 terms. So, this should be A raised power n minus 1. Okay. Let me just do it again so that for clarity. So, when I do this summation A minus 1 goes as it is, A will be the first term, number of terms here are 1 to n minus 2. So, a raised power n minus 2 minus 1 by a minus 1 into b plus ab minus a plus a minus 1. So, a minus 1 cancels with this when I multiply will become n minus 1, this will become a. So, I can actually remove this brace and put a b here, and this goes with this b. So, this cancels with this. You have now ended up with a term a raised power n minus 1 b minus 1. So, in worst case this is the value which you will get, and this is smaller than the operator, the modulo operator here, a raised power n minus 1 b. So, when I do modulo operation, I should get back the same value, which implies that I have L1 prime will be Sn minus 2 a raised power n minus 2 so b I can keep later on S1 of a into b dn minus 1 a plus Sn minus 1. So, that will be the L1 prime. Okay. So, this is the value which we will get here at the after the first shuffle exchange. I can actually now use again the switches and find out what is the value of L2. So, I can use this and find out what is the value of L2. So, let us do that. L2 will be, now I will be, this switches will be doing routing on the basis of digit n d n minus 2. I have to find out which switch, multiply it by b, and then of course plus dn minus 2. So, L2 will now be given by L1 prime by a, the floor function into b plus dn minus 2. Okay. So, this will be, so I can take the L1 prime from there and put it. So, I am dividing by a, so it will become Sn minus 2 a n minus 3 and S1 Tn minus 1 So, I have already divided by a all throughout. So, this a is gone, Sn 1 minus a will be here. Now, all these terms are actually greater than 1, they will all become integer, only this one is a fraction. Sn minus 1 can take maximum of a minus 1 value. So, when I take floor function, this will be going out. So, it will be Sn minus 2 So, since b has to be multiplied later on, so this is what you will get as L2. After a shuffling, you will get so basically at the output here you will have another shuffle, you will get L2 prime here, and you should get L2 prime, let me write it here, L2 into a So, I am just using as q star r I formula. So, you have a raised power n minus 1 into b number of elements here, same will be was present here. So, number of switches which was there a raised power n minus 2 into b. So, number of lines which are going to be here is a raised power n minus 2 into b square. Okay. So, that is the number of QR objects which are present. So, we actually have used that QR divided by a. So, n minus 3, and this has to be then modulo operated over a raised power n minus 2 b square, that is a QR. Okay. So, we can actually do the similar exercise. Okay. So, now let us look at this particular factor as usual as we did last time. So, we will have L2 divided by a raised power n minus 3 b square with floor function. So, I can write down whatsoever is the value of L2 which we have derived and then divide by this. So, let us do that. So, I will have Sn minus 3 sorry Sn minus 2 a raised power minus n3 b square. So, you just expand this whole term and then we will divide by whatever is given here, a raised power n minus 3 b square. So, that was for the first one, then we keep on expanding. Sorry, this is b square. And I have to divide by so this one actually cancels out. So, this one is a complete number. Okay. So, when I take the floor function this will certainly contribute, I have to only worry about this one. So, here again I will do the same thing, I will put SI's maximum value is equal to a minus 1 and DI's maximum value of b minus 1, and let us compute what I am going to get. So, let us write it down here itself, I can do it. So, I will end up in getting a series so all these a minus 1 will come out, I will have a series of a n minus 4, a n minus 5 plus 1 b square, this will be b minus 1 into b, this will be also b minus 1, okay, and then of course divided by a n minus 3 b square. So, this series these actually have terms, total number of terms will be n minus 3. So, if I do the sum up of this will turn out to be nothing but a raised power n minus 3 terms minus 1 divided by a minus 1. Okay. So, I can just replace it here. So, this will cancel with this. So, I can actually remove this one and b square gets multiplied to both sides minus b square. So, this also now I can write b square minus b. So, b cancels with this, b square cancels with this. I have a term a raised power n minus 3 b square minus 1 divided by this. This certainly is less than 1, which implies when I am going to take this floor function, I should only get this term, which is Sn minus 2. Okay. So, I can actually use this Sn minus 2 and put it here, and let us see what is going to happen. So, I can replace this by Sn minus 2. So, I need to expand this one for L2 prime. So, again I will put L2 from there into L2A. So, this will be Sn minus 2 a raised power minus 2. So, remember it was Sn minus 2 a raised power n minus 3. So, I am multiplying by a, okay. And there is a b square term which will also come at the end. This whole thing will be b square plus dn minus 1. So, there is a b, so I have to also multiply by a because of this a. This also has to be multiplied by a. This Sn of minus 2 has come because of this term, and then I have to do modulo of a raised power n minus 2 b square. So, once I do it, so one term which will come out is Sn minus 2 a raised power n minus 2 b square plus the remaining stuff. So, you can see a raised power n minus 2 b square also comes here. So, when I am going to take modulo operation, this anyway has to go out because this will become an integer. So, I need not even bother about it. I have to just check whether what is the value of this, maximum value of this. So, you can actually now do same thing for all SI's, put maximum value is a minus 1, for all DI's put value as b minus 1 and solve and see what you are going to get. So, once you do that, you will have a minus 1 coming out here, obviously. This one will become b minus 1, b minus 1 and a minus 1. Okay. So, once you solve, this series consists of n minus 1 to n minus 3, n minus 3 terms. So, this can now be written as the first term a, total number of terms n minus 3 minus 1 by a minus 1. So, I can replace a minus 1 will cancel with this, b square will come here, So, I can write down this thing as a n minus 2 b square minus a b square. This term will give me a b square minus a b. So, I can replace this. This one will become a b minus a cancels with this cancels with this. You have a term, this minus 1 which is smaller than this. So, when you do modulo operation you should get the same thing. So, the L2 prime will now be exactly whatever is left over here. Okay. Except this particular term which will go out because it turns out to be a raised power n minus 2 b square, it becomes integer multiple of that. So, L2 prime will be from there onward. So, I will have Sn minus 3 a n minus 4 and from there L2 prime, which is here, I can actually again have the set of switches and then get what is the output of that. So, I am interested in what is L3 prime, L3 actually. So, L3 will be now L2 prime divided by A lower floor B plus Dn minus 3. So, this will turn out to be, you divide this whole thing by A and then take the floor function. So, when you divide everything by A, you will get this become n minus 2, this becomes a 1, this here A will cancel, here A will cancel, only thing which is not integer is Sn minus 2 by A, because Sn minus 2 can take maximum value of A minus 1, which implies when I take the floor function this will be going out, rest everything divided by A will be present here. So, I can actually do that Sn minus 3 a raised power n minus 4 plus and so on S1 into B, it has to be B cube now, plus the A will, these A's will be going out. I will have d of n minus 1 b square plus d of n minus 2 b plus d of n minus 3. So, now I can actually use, I have proven this particular expression for 1, that what is the value for 1, what will happen for 2, what will happen for 3, and now I can use induction to prove it for, if it is true for I, it is going to be true for I plus 1, and henceforth I can do it what is going to happen after the nth stage. So, it Li will now be given as Sn minus I a raised power n minus I minus 1, you can actually read C from here, n minus I n minus 3 minus 1. So, from there itself you can derive it, last term will be S1, since it is 3 it has to be b raised power I here plus you will be having dn minus 1 bi minus 1 plus d of n minus 2 b of I minus 2 so on till the last term will be d of n minus I. Okay. So, once you know this, you can always find out what is going to be L1 prime using the same procedure and using same kind of conditions in the maximum values of S and D's. So, this L1 Li prime should be S of n minus I minus 1 a raised power n minus I minus 1 dn minus I into a plus s n minus I. And of course, once we know this, we can find out that what will happen after the nth stage, what will be Ln. So, this actually can be proven using same procedure. So, once you have Ln will now be given as all these terms will vanish and you will end up in that. So, you will have d of n minus 1 b raised power n minus 1, okay, when I will become equal to n, plus d of n minus 2 b raised power n minus 2 and so on, plus d of n minus n, which will be d0. Now, you can clearly see this number is nothing but the output address. You started with this, you connected from any input port, any source port, you keep on doing the same procedure, basically using at every switch one of the digits here will be was used for routing. So, first stage this was used, second it was used, last one this was used, you ended up in going to the same output. So, this Shufflenet is indeed a delta B network. Okay. So, that is a proof which we have.